So let us now go forward to Alok Laddha. Alok, are you here?
Yeah, I'm here.
Okay, can you start by sharing your screen?
Yeah.
Yeah. Okay.
Wait,
Yeah.
I have to do full screen, I think.
Yeah. There is an option, right? You can go to this edit.
Yeah. Not able to, sorry. In the Zoom, should be an option. In the more, I guess.
No. Alok, you should just make it full screen in your, as Sumanta was saying, leftmost thing. Just
okay. Just one second.
Yeah, on your, where whatever your PDF
view,
view.
Yeah, perfect. Okay. So thank you all for the last talk, and this talk will be given by Professor Alok Laddha from Chennai Mathematical Institute. And Professor Laddha will talk about soft theorems and some universal results thereof. So Professor Laddha, please go ahead.
Okay, thanks Sumanta. Thanks to Sriram and all the organizers for all the hard work and also inviting me to speak here. So I'm going to review some work which has happened in the last few years, not just by me, actually, in fact, most of it will be by many others on some new results that we have understood in gravitational scattering, which are interesting from various perspectives in classical and quantum gravity. So maybe I start with some motivation first. So there's one result that I think most of you in this audience will be familiar with in gravitational wave physics, which is what is called the displacement memory effect. So displacement memory, I mean, it's an effect which is an observable effect, and it measures once a gravitational wave has passed after some scattering or some collision, what is called a persistent, which is a permanent physical change in the metric at large distance, at what we call future null infinity. So just to recap, future null infinity is simply a boundary of spacetime which you reach by just following outgoing null judices. And of course, displacement memory is a very old result, from 70s, from the time of Zeldovich, Polnarev, then Braginsky and Thorne, and then there was sort of a qualitatively new understanding of this phenomena by Christopher Lowe, which has been further improved in many ways by Lydia Beery and Garfinkel. And just a little bit quantitatively, the idea is very simple, that you look at the asymptotic metric, which I'm just always going to call HAB for a radiative metric, and you measure it at very late future time, you go to plus infinity at some point on the sky, like at some angle, which we just denote as n hat, and minus the same metric in the far past at equal to minus infinity. And the difference between the two is obtained by looking at it's obtained simply in terms of the incoming and outgoing momenta of the scattering bodies, which we call pi, and the gravitational momentum, finite energy gravitational momentum, which is leaked out at null infinity, which I indicate as A, capital A letter. So A n prime is the linear gravitational momentum, which is radiated at some solid angle n prime, and then we have to integrate over all these angles. And this whole analytic formula is basically the formula for the displacement memory. The first term is what is usually called the linear memory, and the second term is what is called the Christodoulou or the null memory. Okay, so this is an old result, and what is perhaps not maybe that much appreciated is that it's an exact result. It's valid to all orders in the perturbation theory. So once you specify the asymptotics of your system, initial and final momenta, including the initial and final momenta of the massless particles or massless fields, then you just have this formula, and it is not something which is, it's not an approximate formula. So it only depends on the asymptotic momenta of scattering particles and fields. And of course, as it is something measured at infinity, so it's observable, it's gauge invariant. And as we, intuitively we can see that suppose you don't work with Einstein's theory, but you work with some higher derivative theory or something, then what will change as a result of changing the equation of motion is the value of the outgoing momenta, but it will not change the structural form of this memory. And so so displacement, because of all these properties, it's an observable, it's a low frequency observable, because you're measuring the change in the metric between t equal to plus infinity and minus infinity. So it's basically like a zero frequency observable, and it has a certain degree of universality in this sense, that it doesn't depend on the details of the theory and only depends on the asymptotic momenta of the scattering body. In fact, this formula can be written in a nice, little bit compact way as a change in the momentum radiated between at a given angle n hat between the past and the future. So you just look at, with the same formula with little work, we can show that it is, you just look at the total momentum which is radiated in the future at the future null infinity by massless fields and future time-like infinity by massive objects, and minus the momentum, linear momentum flux at the same angle in the past. And this difference is precisely the displacement memory. So this small I plus and I minus are simply the boundaries where the time-like geodesics, okay, and now, but it turns out that this formula actually secretly hides something that we know from other other phenomena in particle physics and in quantum field theory, which can be understood as follows. So as we know that, so this formula basically is the difference, the metric between plus and minus infinity. And so we can rewrite it as I wrote in the equation above. So it's just a total time derivative integrated over the full future null infinity. But we can go to the Fourier, Fourier basis, and then it turns out that this is really just a zero frequency mode evaluated in the way that is written the last term in the above equation. And this idea that the zero frequency mode of the gravitational field is expressed in terms of asymptotic momenta. This is a statement which is known as classical Subgraviton theory. So we will understand more about it, but this is the essence of the Subgraviton theorem, that you look at the radiative metric and you expand it, don't work with u coordinate, u and n hat, but work in the frequency basis. And now you do a low frequency expansion. And clearly the first equation, the fact that the displacement memory exists and it's finite, tells you that the expansion has to start at order 1 by omega. It's only then that the first, the displacement memory will be a well-defined quantity. So that's the expansion. We, just by knowing displacement memory, we see that the radiative metric has the following expansion. We don't know anything about the terms so far, beyond the first leading term, but we know the leading term has to go as 1 by omega. It should be a full term. And what we have recently, the progress that has been made is, we have sort of understood a little bit more about the origin of this universality of this observable, this displacement memory, its relationship with some properties, in fact, of quantum gravity, although these are purely classical observable, and a lot more about these ... terms, which here are, we have just suppressed them. And in last year, we have understood a lot more about them and their universality properties, which is what I want to focus on in this talk. So yeah, just to say what I said before. So we have understood that the displacement memory, in fact, is a first member of a possibly infinite hierarchy of gravitational observables, all of which probe different modes of low frequency gravitational radiation, as we will see. And this hierarchy is encoded in certain exact statements about gravitational scattering, statements which only depend on asymptotics of the scattering and don't depend on the details of the dynamics. And they are known as classical soft theorems. So they are exact statements. They are not perturbative. They will be valid for large impact parameter scattering. They will be valid for mergers, etc. And they will tell you, how to compute low frequency gravitational radiation. And will be fixed by, as we saw in the case of displacement memory, this first term is completely fixed by incoming and outgoing momenta. As we will see that there are other terms which will be fixed by not just outgoing and incoming momenta, but outgoing and incoming angular momenta. But they will all be independent of what happens inside the space-time, like what is the exact details of the of course, we can ask, like, why all this, if this is true, then why is this true? Why these results are universal in the sense they don't depend on the details of the dynamics. And it's kind of reminiscent of conservation of momentum and angular momentum, right? That which don't depend on details of the dynamics. Just these things are conserved. And so it turns out that even this universality that we will discuss is actually tied to a group of infinite dimensional symmetries of gravity. And part of this infinite dimensional symmetry has been known since 60s, which is known as this Bondi-Meissner-Sachs group. But now, thanks to these classical soft theorems, we are actually understanding more and more. There are many more symmetries, perhaps, of classical gravity. And finally, these results have interesting, in fact, very precise quantum counterparts, as we will see. So just to say it briefly, that in quantum theory, of course, we compute probability amplitudes. And if you look at probability amplitude for emission of, low frequency graviton, then it turns out that probability amplitude, if you know that form, which we know from many, many decades, we can use that and take some, in a very nice way, classical limit to derive classical soft theorem. So there is a three-way relationship which is in last few years becoming very, very precise, in fact. And it's captured by this abstraction known as the IR triangle. It's kind of a abstraction which relates three seemingly different quantities. One is the low frequency gravitational radiation. One is symmetries of gravitational scattering, classical gravitational scattering. And one is certain infrared properties of scattering amplitudes in quantum gravity. So what we will try to do is to explore some aspects of this abstract object infrared triangle in this talk. So if there is any question anytime, please feel free to stop. So let me just first give you some setup of the kind of scattering we will deal with. So we just start with some class of initial objects. I mean, for our purpose, they are particles, but they are bodies. So they can be black holes or neutron stars. So they may have many other multiple moments, but as you will see, the only ones that matter for us are the mass, the linear momentum, and the angular momentum. So we start with some collection of initial objects with masses, from M1, P1, J1 to mass, linear momentum, and angular momentum, M and P and J, and they scatter into some K outgoing objects with similar with this momentum, mass, and angular momentum. And of course, in addition, generically, the outgoing state may also contain some finite energy gravitational radiation. And what we want to do, what we want to study is really the outgoing radiation at very late time. So that's our goal, because late time is low frequency. So our goal is to understand, compute this low frequency gravitational radiation. And maybe more quantitatively, what we want to do is to compute what is called the radiative field, the gravitational field which falls off as 1 by R, in retarded time. And then, it can generically has two polarization, which I'm just denoting as plus and cross here. And we want to compute it at frequency omega and at solid angle n hat, where omega is small in a precise sense, and small in the sense that if you have scattering involves some impact parameter b, then omega b should be very small. Or if it involves bunch of particles with mass m's, then omega by m mi, where mi is the smallest mass, should be very small. So this is the sense in which we are doing a low frequency expansion. So all other scales in the theory, mass scales in the theory, they dominate over the frequency. And this is the object we want to compute, is h omega n hat for this range of omega. And so let me first give you the result, and then I will give you some sketch of how this result is derived. And it's quite fascinating. So in fact, I'm giving you a structure which is actually true not in 4 dimensions only, but in generic d dimension. And so let's just look at all the terms carefully. So there is the overall, the phase the I omega r. So I'm looking at this radiative field at a large distance r. So it falls off, it's a radiative field, so it falls off at the rate d minus 2 by 2. If d is 4, then it falls off as 1 by r. And then there is some phase which always accompanies the
9:30.
Is there a question? Hello?
Yeah, I don't see Alok.
No, Alok, please go ahead. There was some
I
disturbance.
heard some sound, sorry.
Yeah, there's some disturbance, please.
Yeah, so this radiative field is what we want to compute, and we want to do the small omega expansion of the radiative field. And it turns out that this has the first term is of course what we discussed before, which is the displacement memory, which goes as 1 by omega. But there are a host of other terms which are colored differently. So the red term, which is which goes as omega to the 0, it's a term which is, again, as we will see, it is universal, that is independent of all the details of your equations of motion, and it's universal and exactly known in all dimensions greater than. So and in d equal to 4, if you there are some caveats, but if you assume that you are in a weakly perturbative regime, then this term again turns out to be universal to certain order in perturbation theory. And in literature, in gravitational waves community, this term is often called the spin memory or the center of mass memory. So these are these new memory observables that people have discovered thanks to this analysis of gravitational soft theory. So and we will see more about exactly what the form of this term is. Now the blue terms are perhaps the most fascinating. They exist only in d equal to 4. They are completely universal. They don't depend on the details of the theory. And they are tied, as you could guess, because of the fact that there's a log dependent on the frequency, that are tied to the 1 by r infrared effects in 4 dimensions. The first of this term, which is n equal to 0, so that is a term which goes as log omega, that is actually known perhaps not in this form, but it was known certainly from the time of Damour and Blanchet's paper in 91, and it's known as a tail to the memory in the gravitational system. And all the terms which I have not written, like the order omega log omega terms, although you can compute them, they are not universal. So they change, depending on the details of your dynamics and the details of what order you are in the perturbation theory, etc. So they are not universal. But so that the key focus of our talk is our discussion today is the blue and the red term. The first term is already known. Now, the most direct proof of classical soft theorem is, in fact, it may be surprising that how we can prove these things, but it turns out that the most direct proof already you can give in a classical theory. And to simply analyze low frequency gravitational radiation for just generic matter of particles plus finite energy massless fields, just using retarded Green's function. You may think this is not possible, but it turns out that because we are interested in only in low frequency radiation, you can in fact derive these terms exactly. But what we will do is not go through this proof, but we will sketch a little bit different proof, which has a interesting added advantage in some sense that it makes connection with some properties of quantum gravity manifest, which is quite interesting. Okay, so suppose so you want to compute a classical quantity like this radiative field, but let's say you want to compute it for some masochistic purposes from quantum theory. So for some reason you want to go first quantum and then take classical limit. So you start with some coherent scattering state, of course, because you are doing classical analysis, which is like a wave packet, which is composed of, say, a collection of massive and massless particles. And then, okay, in principle, formally, we can compute the any classical observable in the future via a formula, which I have written in the above, below, which is that, if I want to compute this radiative field at frequency omega and at solid angle n hat, then all I have to do is to evolve the in state to the out state by the S matrix of the theory, and then compute the expectation value of the graviton field operator, which I have just denoted as h hat, and then take the h bar going to zero limit. And it turns out that the thing in this expectation value is actually, in fact, nothing but the transition amplitude, where you take your initial particles with some momenta p1 to pn, they go to final particles from momenta pn plus 1 prime to pn plus k prime, and an added graviton, which has a momentum which is omega n hat. So remember, if omega is given and the direction is given, then we know the 4 momentum of the graviton, which I'm just denoting as omega n hat. So if you can compute this amplitude, which is usually very hard to do in quantum gravity, of course, and then you can take the h bar going to zero limit, okay, in principle, you will recover the radiative field at any frequency, at any solid angle. But this itself is not, it is not something which is immediately very useful, because quantum computations are usually harder than classical computation. But what these authors, Kosovar, maybe and O'Connell, proved in a really beautiful paper in 2018 is that if you take this h bar going to zero limit, in some sense as early as possible in your quantum computation, then it turns out that you can use a lot of tools of the scattering amplitude, which are very, very powerful, and they can be used to compute classical observables very, very efficiently. So of course, this is only true as long as you can compute the amplitude, which is usually true only in perturbation theory. So these proofs that I'm sketching are only true. They are not true for mergers, for example, but they are certainly true if you have a large impact parameter set. Whereas just to clarify, the classical proof is completely universal. It doesn't depend on the fact that your scattering is perturbative or anything like that. So it's a much more powerful proof, but this one brings out nice connection with quantum gravity. So okay, so let me first start with the universal results in the greater than 4 dimensions, because they are simpler to understand from this perspective. And in their case, actually, it is known that the amplitudes in quantum gravity or the S matrix in quantum gravity, they satisfy certain factorization properties, which are called quantum soft theorems. And again, these are theorems which have been which are slowly being discovered. I mean, the first of this theorem was known in 60s, and then subsequently theorems were proved in last few years, especially by Ashok Singh. So the essence of the theorem is what I have written below. So if I have a transition amplitude involving some matter particles with momenta pi's, and then a quantum graviton with frequency omega and direction n hat, then it turns out that this amplitude can be factorized into an amplitude without the graviton. So the amplitude on the right hand side that only depends on the other particles, times a factor. And if you look at the first factor, it will look to you very familiar, like very similar to the displacement memory effect. So that term goes as 1 by omega in this omega expansion, and it depends only on the momenta of the scattering particle. But the second term is a bit more interesting. It is a term which goes as omega to the 0. It depends on the linear and the angular momenta of the scattering particles. And angular momentum is an operator, of course, in the differential operator in quantum mechanics. So I put a hat there. And these are the only two universal terms in this expansion. So, again, if we can go to the next order in omega, we can compute it, but then that term will depend on the, whether we are in what order we are in perturbation theory, whether we are looking at Einstein theory or higher derivative theory, etc. etc. So these are the two universal terms we have in the for the S matrix, in any dimension greater than 4. So they are exact, is just what I said, and they are valid in any quantum theory. In fact, any theory of quantum gravity. And in some sense, the only assumption we need here is that it should admit the Minkowski vacuum as one of the solutions of the theory. And these factors have some names. So the first term is what is called leading a Weinberg-Soft factor, and the second term, which was discovered first for a very simple class of amplitudes by Kachazo and Strominger, so it's called a Kachazo-Strominger soft factor. The proof in full generality was given by Ashok Sen in 2007. And again, these other terms, which are order omega, they do factorize in the same sense that we can again write the next term as some factor operating on the amplitude without the graviton, but we are not writing them here because they are not universal. They depend on the details. Now what? Okay, so now we are in a good place in the sense that we can take this amplitude and we can substitute it in this KMO formula for the classical limit, and then we can try to derive the classical radiative field at least at low frequencies omega. So here we are using, of course, the soft expansion of the amplitude, and so this is something that you can do, and then it turns out that you can derive two results. The first result is you just reconfirm the fact that the leading order term will give you the displacement memory effect. And in fact, this was actually derived in a very nice paper by Haridas and Soni way back in 82. Of course, they didn't use KMO or anything, but they had some other arguments to use Weinberg-Soft theorem to derive classical gravitational scattering. So we basically get two terms. The first term, by using this approach of quantum soft theorem, we get the first term, which is the displacement memory effect, and we get the second term, which is quite interesting. We get a term which, as you can see, depends on the initial and the asymptotic momenta and the angular momenta of the scattering particles, the incoming and outgoing particles, and a term which is like very similar to the nonlinear memory effect in the displacement case. So it is determined by the finite energy gravitational flux which is leaking out. So this B mu nu n prime is the angular momentum flux which is emitted at solid angle n prime. And this it is this second term, like it is this kind of similar to the Christodoulov term, nonlinear memory term, which is what is often called the spin as well as the center of mass memory. And I think this term has now generated a lot of interest even in four-dimensional analysis, especially by Tucholsky and Wittmann, Nichols and just to summarize so far what we have. So then in D greater than 4 dimension, by using these ideas of Kosover et al. And using the exact results in quantum S matrix, we get a formula, one new universal observable, which is which is the next order term in the soft expansion of the radiation, which is this term that I have written, this H0 mu. So okay, so the reason that this result is universal is simply because we derived it from the quantum soft theorem, which is universal. So that was the main advantage of, in some sense, using the quantum analysis, that we have some exact result which is valid, even in string theory. So of course we can use it in class as an exact statement, and then we take classical limit and we get this. Okay, so now this was in D greater than 4, which is not, okay, it's not immediately interesting for us in some sense. So we want to go to the D equal to 4. So we already know one thing without doing any analysis, that the leading classical soft theorem is same as the displacement memory. But we would like to know what happens to the second term, which is the the new observable that you have found, which is subleading term in the soft expansion. And it turns out that this one actually gets deformed in a rather subtle way. So just to illustrate what happens, I'm going to focus only on the contribution from the linear, maybe the linear spin memory. So the contribution only from the massive particles. So I'm going to ignore for a moment the gravitational flux contribution, which is the second term in this expansion. And you can already see what will, we just stare at this term, we can see what will go sort of, what will start changing. So we know that because of the 1/r effect in 4 dimension, if you look at the asymptotic trajectory of any particle at late time, I'm sorry, I forgot an equal sign there. So x nu t should be equal to in the large time limit. It has it will have the free trajectory part because at late time particles go far away from each other. But because of the fact that there's a long range Coulombic interaction, particles are never really completely free, and there is a logarithmic acceleration term that always persists in 4 dimensions. Something very specific to 4 dimensions. And in fact, people from particle physics community will immediately recognize that this is actually tied to the fact that in 4 dimensions the S matrix is infrared divergent as soon as you have in gauge theories and gravity. But if if there's such a log divergence in the asymptotic trajectory, and if you just even naively compute the asymptotic orbital angular momentum for these particles, which is a quantity which directly features into the the h0 mu nu, which is written above, then we will see that obviously the angular momentum will also diverge as log. So just to be a little more quantitative, I mean, if you just compute the late time in the future and past the orbital angular momentum, then it will have a divergent pitch which goes as log t. And okay, now if I just blindly substitute this in the formal expression that we actually derived in higher dimension, which is the one written in the red bracket above, then we see that it looks like the term which was going as omega to the 0 in higher dimension, in fact, diverges as log t. And this looks like a little bit strange term. Like, I mean, what does this mean? So we could make an educated guess, which is what we did a few years back. And we said that, okay, because this log t is at late times, maybe we can, and we are interested, we are of course doing a frequency analysis at soft, small omega. So most naive thing you would try is to replace log t with log omega inverse, because late time is same as soft frequency. And then, okay, so that gives us a proposal for a universal term in d equal to 4 dimension, but it's something that doesn't go as omega to the 0, but goes as log omega in the soft expansion. So, okay, so that is one proposal. Of course, this proposal we have to check at least and also hopefully prove. And the proposal is that we have instead of the spin memory term that we got in higher dimension, we have this new term, which is a log term. And this term depends on the asymptotics again. It depends on this acceleration C, asymptotic acceleration term C, and the asymptotic momentum. And first thing we can do before we try to prove it is to maybe test it in a variety of examples. And thanks to a lot of work by relativists in early 70s, we already had some catalog of results we could use. So the most famous one, which was also in some sense the most powerful one, is the work by P.C. Peters, in which what he does is he derives the so there was a paper he wrote, I think in 78, in which he derived the radiation. So he took a probe particle which is scattering in Schwarzschild spacetime. There's a back reaction, and because of which there's radiation, and then he computed the radiative field at any frequency omega. So of course you cannot analytically compute it at any frequency. So he had this messy analytical integral expression for the field, but he had an expression which had a lot of integrals, etc. So what you could do is you could take a soft limit of his expressions, and we indeed checked that the result that we got confirmed our proposal. So that gave us some confidence in our proposal and then there were some other examples that we tested. So we can in fact we can see like what are the consequences of this new term in time domain if you go from frequency domain. And so it turns out that in the frequency in the time domain, the first term, of course, the displacement memory term is something which goes as which persists at infinite time. So it goes as it is something which is staying at equal to plus infinity. And the second term, I'm sorry, there's a typo. This should just be h log by 1 by u. It should not be the dots there. So the second term, which is the log omega term, if you use Fourier transform log omega at small omega, it's just 1 by u. So the second term is something which is decaying at you go to infinity at the rate 1 by u. So it's what is called tail to the memory, because it kind of tells you how the displacement memory builds up this log term. Okay, and in fact, there was some interesting thing we observed that if the outgoing particles are all massless, if you take the same formula we have, but you assume that all the particles are massless, we can still think of them as particles instead of fields. But let's just assume they are all moving with speed of light. Then it turns out that this term exactly vanishes. So if you have if you look at a case where you have a black hole binary merger where the mass of the okay, it's a very fictitious phenomenon, but the mass of the final black hole is much smaller than the mass of the initial black holes, and most of the energy is carried out by radiation. Then this tail to the memory vanishes, and this cancellation is something that still what is the precise origin of it is still not understood. So okay, but we haven't proved it. I mean, this is something we just tested. We gave a proposal and tested it. But in a very beautiful work in 2020, Saha, Sahu, and Sen in fact proved it from asymptotic analysis of equation of motion. And because the proof really only depends on the asymptotic analysis of equation of motion, it doesn't assume anything about the scattering. So the scattering it's valid for any class of scattering. But again, for curiosity, we can ask that the way we did the proof for the H0 in the higher dimension, can we, at least for large impact parameter scattering, where we can apply perturbative techniques, can we use the quantum amplitudes to derive this result? And it turns out that indeed that turns out to be true, at least in perturbation theory. That you can use again the soft theorems, quantum soft theorems, and you can show that the classical limit produces for you this tail to the memory. So Sumanta, maybe I can ask how much time I have. Sumanta, can you hear me?
Yeah, you probably have about a few minutes, 3 to 4 minutes, Alok, and
okay,
then
great.
you can leave a few more minutes for questions. Yeah.
Okay. Yeah.
Thank you.
I'm almost done. So in fact, in the same paper, Saha, Sahu, and Sen conjectured that in 4 dimensions, so in higher dimension, we have only 2 universal terms, the displacement memory, the spin memory. But it turns out rather remarkably that in 4 dimensions, we get a hierarchy of these universal radiative observables, and this is the expansion that they had proposed. So the first term is the displacement memory. Then if you take n equal to 0, that's the tail to the memory that we just discussed. But at every order n, you have a tail to the tail and subleading tails, and these are all very complicated expressions. But so we can't. I mean, they go several lines on a page, but they only depend on the initial and the final linear moment of the scattering object, and they don't depend on anything else. So something that I didn't explicitly say it here, but here if you just look at the CIs, then the CI is completely fixed by the asymptotic moment of the other particles, because it's the Coulombic drag of the other particles. So in the end, this expression only depends on the linear moment of all the particles which are scattering. It doesn't depend on anything else. And in fact, it turns out that this property remains true actually for all the subsequent terms also in this expansion. So this is quite a striking proposal, which has now been proved to next to leading order. So that's the n equal to 1 order in this equation by Vishwajit Sahu, that you have this exact universal terms in the soft expansion of the radiation. Okay, so I don't have much time, so I will just tell you a little bit more about now. As in the beginning we discussed that there was a triangle, the 3-way relationship between the classical soft theorem, quantum soft theorems, and some symmetries which we didn't really talk about. So I just want to tell you roughly what these symmetries are, so that we have some idea about this infrared triangle. So of course we can ask the question, why does gravity have so many radiative observables at low frequencies? I mean, whose form is completely determined only by the asymptotics. And the first thing we can do to understand this is to write the displacement memory in the way I sort of wrote in one of the initial slides. So the displacement memory can be simply thought of as the flux of momentum which is emitted at the solid angle n hat in the future minus the flux in the past. And in fact, it turns out that this formula can be written in a very simple way, which relativists know very well. It is simply you take the Bondi mass aspect, which is the density of mass at a given solid angle, and it's simply this formula can be thought of as infinity of conservation law.
Yeah, you have 5 minutes left.
Yeah. Okay, thanks. Thanks. Yeah. So I will be done. Yeah. So the mass aspect at u equal to minus infinity. I'm sorry, in the right hand side it will be v equal to plus infinity. So the mass aspect at v equal to plus infinity in the past is equal to mass aspect at u equal to minus infinity at any solid angle n hat. That's just the rewriting of the displacement memory formula. And so now this is a conservation law. In fact, infinity of conservation law, in the sense for every solid angle we have a conservation. And it was shown by Strominger that this conservation law can be obtained from a known symmetry of gravity, which is called the supertranslation symmetry. So since we don't have time, I won't go much into it. But even though the symmetry was known people hadn't realized how to use it to derive conservation laws in scattering, something that Strominger initiated. After that, a lot of progress was made. I mean, in this direction. So at least we see that there is a three-way relationship between a specific class of symmetries called the supertranslation symmetry, the displacement memory, which is a classical observable, and the Weinberg-Subgraviton theorem, which is a property of the quantum gravity amplitude. And they are the facets of the same universal object. And it turns out that if in 4 dimension, if we assume peeling, which is actually not a very good assumption, it's a rather strong assumption, then you can at least express this spin in the center of mass memory, the H0 term. So it will remain valid if you assume peeling, and you can express it as a conservation law for the angular momentum aspect. But no one has been able to prove that this angular momentum aspect is conserved even if you assume peeling. And of course, we know certainly that 4-dimension peeling is generically violated as soon as we have massive particles. This is something that Christodoulou Damour showed long back. And the way this peeling is violated is that if you look at the asymptotic form of the metric, then it has these new terms which go as log r. They logarithmic diverge with r, and there is a tempting hint that maybe the new conservation laws which we are getting in the new observables we are getting in 4 dimension, these log tails, perhaps they are related to these terms which are violating peeling. So we don't have any evidence understanding so far in gravity, but in electrodynamics, where much of this structure also persists, we have some evidence, some earlier work. So that's it. So I just end here. Thanks a lot for your attention.
Thank you very much, Alok, for such a nice presentation. It's now open for questions. And I can see Sumati Surya has a hand up. So Sumati, can you please go ahead and ask?
Yeah, thanks, Alok. Very nice talk.
Hi, Sumati.
Hi. So I'm going to ask a question about quantum gravity here. Yes. This is something that puzzles me in much of these discussions, which is that you're really talking about an infrared effect. And you also state explicitly that it's quote unquote independent of the theory of quantum gravity, yes, except for certain assumptions.
Yes.
But in which case, why is this simply not a classical effect? I cannot see where quantum effects.
It's not a classical effect in the. The classical observable is of course the classical effect. You're talking about the quantum soft theorem. Is that the?
Yes, I guess in particular, what you mean by quantum gravity soft theorems, right? I mean, we're not.
Yeah. So that is certainly a property of the scattering amplitude. So in the sense that you take the scattering amplitude, for example, just to give an example, at any order in loop expansion. And then the statement is that it is of course not obvious that at any order in loop expansion, if you do a expansion of the amplitude in the frequency of the emitted graviton, then it would have this kind of nice factorization.
Right. But this is already an assumption that there exists a theory of quantum gravity, which is well defined with graviton scattering and so on and so forth.
Yes,
so this part I don't understand.
Yes. So that is the assumption that I stated, that we assume Minkowski vacuum. I mean, that's one thing that we assume for the property. So it's a property, for example, which is satisfied by string theory, and there we know that there are gravitons, of course, excitations over the Minkowski vacuum. So certainly I agree that the existence of gravitons, of course, that was the assumption that I also stated, that we assume that there is.
No, but not just that the existence of gravitons, but also that theory has a well-defined, that theory is well-defined in the precise sense of the word.
Yes, that's a very good question actually. So in greater than 4 dimensions, and if we had an asymptotically flat setting, then we know that at least formally S-matrix is a good observable, because it's something that is computing the amplitude to go from the past to the future. So it's something that is only defined on the boundary, so it doesn't depend on diffeomorphisms, right? But now, of course, it is true that we don't know if S-matrix is a good observable, in the sense we don't know if it's well defined or not. And if you take a UV complete theory like string theory, perturbative string theory, then you know that at least in the UV, this S-matrix is well defined. And now the question is whether it has a good infrared limit. And it turns out that this is where the higher than 4 dimension issue entered. So, it is in higher than 4 dimension, S-matrix is well defined, in the infrared as well as in the UV in string theory, for example. And then we can actually ask this question that if we take a soft graviton expansion, soft frequency expansion of one of the gravitons, then how does the amplitude behave? just to say it a little bit another way, which maybe address your question, is that if you just look at this quantum soft theorem, then let me just go back once. Formally you can think, if you just look at the first term, formally you can think that what these soft factors which we have written, the 1 by omega term and the j term, is like a ratio of the two amplitudes. So it's the ratio of the amplitude with one soft graviton and the amplitude without the soft graviton. And it can in principle happen that even in 4 dimensions, it can happen that individually these amplitudes have infrared divergences, but it could happen in principle that the ratio is in fact finite. And that is indeed what happens in 4 dimensions. So in 4 dimension, I didn't write down, but there are these quantum blocks of theorems, which I didn't have time to talk about, which are well defined and finite, even though the amplitude itself is I divergent, because they are really ratios of the amplitude. So there's a precise sense in which these quantum soft factors are well defined, and they are really properties of quantum theory. I don't know if that answers your.
No, I'll take it offline later.
Okay.
Or online later.
Or online.
Later.
Yeah, there is another question by Srijit. Srijit, can you unmute yourself and ask?
Yes, thanks, Sumanta. So Alok, could you please elaborate a little bit about the statement that you made in your earlier part of your talk, that this displacement memory is gauge invariant since it is obtained in the boundary?
Yes. Yes.
What exactly?
I just meant the fact that it is displacement memory is just the zero frequency mode, as of the News tensor. And News tensor is gauge invariant in the sense that News tensor is a quantity defined at null infinity. And if we think of gauge transformations as those which diffeomorphisms which die down at boundary, small gauge transformations, then trivially it's a gauge invariant observable. That's all I meant. Yeah.
Okay. So, but anyway, this symmetry is like super translations are probably realized as large gauge transformations.
But they are not gauge in the sense that if you compute Noether charge, as of super translation, that is not zero. So
yeah.
So that is why super translation.
Yeah. So another related question is that what I know from the literature that there are various schemes to calculate the charges, and the charges are not unique in the sense that it is some sorts of scheme dependent probably, because in some scheme the charges are finite, and in some other scheme the charges may become even zero. So can you
so my understanding is super translation charges are fairly unambiguous. I think you may be referring to the
super rotation charge. Yeah, I am talking about.
So that is yes. So we can have a much longer discussion about the angular momentum aspect as you are discussing. For super translation, there is no problem, and for the angular momentum aspect, there is no unique definition. There is, what we know is that there are 2 parameter families of definitions for the angular momentum aspect, but yeah, we have to discuss more. If you demand that we want to look at that definition, which gives you a conservation law between scri minus and scri plus, for example, then there is a definition. I don't know of any other. I mean, there is at least one definition proposed by Miguel and Compare that satisfies the conservation law. If you do not worry about conservation law, if you just want to define angular momentum aspect at scri plus or scri minus, then there is a lot of ambiguity. But perhaps it's reduced if you ask that you want to look at the angular momentum aspect which is conserved. But I should insist that we don't know whether conservation, no one knows how to prove the conservation law for the angular momentum aspect.
Yeah. Okay, thanks.
Thank you very much, Srijit, for your talk, and thanks to Alok. I think it is time for a coffee break, not in offline mode, but at your own places.
Thank you.